went and took 15 minutes of my time. So now we're going to zoom in and see what else we can use these for, this method. We've just calculated diet in a straightforward way. Okay, wood rats. These wood rats, we would just put them in a jar for a couple of minutes and sample their breath. Okay, so there's an inflowing air and we have outflowing air, and we can use this to measure different things. What we are interested in is looking at, in this case, the delta O18 of the breath. So all we had to do, the breath is an isotope equilibrium with CO2. It's perfect. Okay, and the CO2 is in equilibrium with water, your body water, so you just need the CO2 that's coming out. It's fantastic. So it actually, the inflowing air just had CO2 stripped out of it, so the CO2 going out was in isotope equilibrium with this animal. So here's 3 different individuals, and you can see one is a switch from negative to positive, one is from positive to negative. And using this notion, the reaction progress model, we can actually plot both sets of data on the same diagram, and we get one linear line. So in this case, a turnover about 3 days. So again, this is really valuable where you've got limited samples. Okay, if you can combine experiments that actually have different isotope initial and end points, you can actually combine them because you just need to renormalize. So you're going to initial value, call 1, final value, call it 0, and you can do that. So it's simple if you do that. This is actually just a dry down experiment where we were trying to figure out what the half-life of water is in an equilibration experiment in the lab, a day and a half. This is the original way the data was presented in a classic paper of Brazilian soils turnover. Again, but in reaction progress, you can again plot it the same way. Our question was there several components? And we couldn't tell whether or not there was. It looked like if there was pretty minimal. Here's a really interesting one. This is the experiments that had been done for quite a long time. So the bird people are really interested in knowing where birds were before they started their trip. So they will catch a bird somewhere and then measure the blood and say, oh, well, based on the turnover, because it's eating something here now, where might it have come from? Okay, so this is some data by that Dave Podlasek published. Dave started working with us just after this. He started working for us in the next year. And we said, well, here's the red blood cell data that they had published, okay? And they published 255 hours, 11 days, as the turnover time for the red blood cells. Well, now let's re-look at the data in the reaction progress model. And here's the turnover, and oops, it does not intercept 0. It actually has a delay time. Nothing happens for 84 hours. And why doesn't anything happen for 84 hours? Okay, you get your turnover red blood cells. You're sampling it in the blood. How come nothing happens? Where are red blood cells made? They're made in bone marrow, so they're not made there. Okay, that's like saying, you know, we're going to see what the residence time of cookies is when you guys leave this room. So what is your 0 time? When you guys leave the room or when Ming puts them out there? She's already got them out there. So do we count the 20 minutes? We shouldn't count that. So this tells us that this 255 hours actually is 2 different things. There's this delay. We can actually use this to figure out how long the average it takes to actually make blood cells and what the true half-life is. Okay? So and so we went through the literature and we found that every single bird experiment had missed this. And the worst part was, every single bird experiment had done their sampling at the wrong time, because when do you want to do your detailed sampling? You want to start your detailed sampling here. Okay, so the typical way of doing the sampling for this sort of project is you sample on day 1, day 2, day 4, day 8, day 16. Well, when you do that, you missed all this really detailed sampling should have been done during this interval. Okay, so again, you can actually rethink as to how you're going to design your experiments. When should you be doing the real detailed sampling? And rather than just at the instant of diet switch, if you know a little bit about this turnover time, you can actually get better detail in here, which is where we really needed the detailed data. Yeah, so that's the point, is we just we can use these reaction progress things to design our experiments. And there's other things that you can do. Here's again some data. Okay, this is some data on llamas that we did. And again, you can see, oops, same thing sort of happens. The animal, depending on the animal, we can actually quantify the delay time. The delay time for horses is about 5 hours. The delay time before anything shows up in a ruminant animal is actually about 35 or 36 hours. Okay, so here's our delay, and here's our turnover time. All right. We can use it to correct for growth, and that just means you put in a R term. Okay? So this is just an example where you look at the weight of fish, and here's the growing fish, the non-growing fish. Here's the nitrogen values, and if we correct the nitrogen value for growth, we get actually a different turnover time. Okay.